So one way to set this problem up is to look at the ratio of the defective to the sample and then compare that to the ratio within the population. So what we could say is that we know that there are 75 switches in the sample and 2 defects. So in the sample, we know that that was 2 out of 75. And then in the population, we know that that's some number out of 3,000. And we know that these have to be equivalent fractions if we're assuming that we did a random sample. That's the whole point, is that we can theoretically determine what that value should be. So we would set these two ratios equal. So we'd say that 6,000 equals 75x, and we get that x would come out at 80, which means that we would expect out of the 3,000 switches that were made, that 80 of those would be defective. Now let's look at the light bulb problem. We can use the same idea to help us with the light bulb problem. Here we know in our sample that 2 out of the 60 light bulbs were defective. So we can do 2 out of 60. And we know our population is 1,728 light bulbs, and we don't know how many of those are defective. So again, we can set up a proportion and solve for the number of defective light bulbs. If we do this, we would get 3,456 equals 60x. We divide both sides by 60, and we get that x equals 57 6/10. So that means about 58 bulbs will be defective. Now in the last problem, again, we can follow the same idea here, where we know the sample. So we just found it and said that it was 2 out of 60. And we know this case, our population, well, they tell us here that we're looking at 144 bulbs in each box. So now our population that we're considering is 144 bulbs. So we're going to start with our sample ratio and set it equal to how many bulbs out of the 144 we expect to be defective. So we would have 288 equals 60x. X would equal 4 8/10. So we would say about 5 bulbs in this case would be defective in each box.